Welcome everybody to the latest episode of What's New in Dorado. It's hard to believe, but it's been 3 years since we first introduced Dorado right here at London Calling, sharing our vision for the future of base calling. Dorado is Oxford Nanopore's engine for both primary and secondary analysis. It started as a base caller, but it's grown into a comprehensive toolkit designed to scale with modern GPU architectures and your research needs. Since introducing Dorado, we've continually added major new features. It now includes an extensive set of modified base calling models for DNA and RNA, barcode demultiplexing, alignment, poly-A tail length estimation, adapter and primer trimming, read correction, assembly polishing, and as of yesterday, Dorado now includes a variant caller, a feature that my colleague Ridian will cover in more detail in the next talk. Dorado is available as a standalone command line tool, available on Linux, Windows, and macOS. It's open source and on GitHub, and Dorado is the integrated base caller that is in Minnow. It's also available via the WF base calling workflow in Epitome, and all of the features from today's talk are available right now. It will also be added into Minnow 2509 later in the summer. Another great improvement we've made this year is we have published thorough documentation on Read the Docs. This is now the best place to go if you want to learn how to use Dorado and explore its features in more details. Just yesterday, we released Dorado version 1.0. So let's take a look at what's new. The big new feature in this release is Dorado variant for SNP and indel calling. We've added more capable DNA and RNA base calling models, and we've significantly improved the speed and accuracy of modified base calling. This release introduces 4 new mod models with 2' methylation detection, and we have also deprecated a few features. We've removed support for some of the older conditions, and we have dropped support for Fast5 input. Conversion tools for Fast5 to Pod5 will continue to be available, however. In many of the major Dorado releases, we introduced new base calling models, and with this release is no different. We're introducing the v5.2 models. Our super accurate model delivers 99.75% accuracy, single pass, that's Q26. But for many applications, we do recommend our highly optimized hack model. And in this release, it's been improved by 1.4Q, an error reduction of over 25%. The v5.2 models are also significantly improved in 6MA-rich sites, making them especially useful in chromatin accessibility applications. Dorado continues to go beyond canonical bases, offering deeper biological insight. We've updated all the modified base calling models in this release and introduced some new ones. And as with the canonical models, these new models are more accurate and push the state of the art for modified detection further forwards. All the models have had a major emphasis on improving their false positive rate, and remarkably, the 6MA all-context model has improved from Q16 to Q24, and note again, these accuracies are single-site, single-strand detection. With RNA mods, we've expanded our direct RNA modification capabilities with the 2' methylation, a sugar phosphate backbone modification that affects stability, folding, translation, and immune recognition. It can occur on any of the 4 bases and is found in both coding and non-coding regions. Modification detection uses separate deep learning models at each site, which can be especially costly in our all-context models. And in version 1 of Dorado, we have re-engineered mod calling to use new model architectures and hand-optimize the code so that the maximum performance is achieved. And we can take a look at 2 examples here. 5MC, 5HMC is now 4 times faster, and 6MA is 7.5 times faster. And this is at the same time as those error reductions shown on the slide before, 6MA being 85% reduced. Gordon touched quite a lot on compute in his intro opening the show, so let's talk a little bit more about compute. Base calling relies on machine learning models, such as those found in ChatGPT or Gemini, and these models are compute intensive and require modern GPUs. But GPUs have been improving at exponential rates over the last 10 years for these types of applications. AI inference performance has grown over 100x from Pascal to Hopper, and Dorado leverages these improvements. We see this in the base calling throughput from single-digit gigabases a day processed on Pascal, which is NVIDIA's GPU from 2016, to over 100 gigabases a day processed on Hopper. And I'd like to thank Rasmus Kierkegaard for his crowdsourced community benchmarks here. And in version 1.0, we have further increased the submodel performance up to 40% on Hopper and Blackwell, with more Blackwell optimizations coming. Last year, we moved to transformer architectures for our V5 submodel, and since then, we have shown that these architectures scale extremely well for the base calling problem. I don't have time to cover the transformer architecture today, but please, if you're interested, go back and look at Sam Davis's talk from last year on this topic. Now, if you look at the plot shown here, the required inference compute is on the x-axis, i.e. the base calling time required, and on the y-axis, we have the accuracy. And if you see here, we have a linear trend showing that as the model capacity increases, so does the accuracy. I want to point out that this is on our fixed released condition. There's no chemistry here. This is all just compute, and we can see an increase from our submodel at Q26 to Q28 and beyond. So with GPUs getting faster and our signal data being rich, we are introducing a new class of model in Dorado. This model we are calling the Hyper model, and it's a Q28 plus single pass, single strand model. It's available today, and it runs on Hopper and Blackwell GPUs. And if you're interested, you can apply via the register your link QR code available on the slide. Thank you.